Hey guys, welcome back to Chemistry 1032 Blended Class Instructional Videos. I am your professor, Dr. Russell Betts, and I'll be taking you through the rest, I hope, of Chapter 4 in this part. If the video gets a little long, we will make a Part 3 for Chapter 4, but I do think we'll be okay. Now, without any further ado, let's jump right back into where we left off. Chapter 4.4, we'll be talking about atomic number, and we'll be talking about mass number, two different but related things. Atomic number, write this down, is a whole number specific for each element. That's an important concept. It's a whole number. It's never a fraction. You're not going to have a decimal point there. It's a whole number. It is the same for all atoms in an element. So for example, in the atom element gold, every gold element has the same atomic number. Every atom that makes up a gold ring is the same atomic number. And what is the atomic number? It is equal to the number of protons. So it tells me how many protons are in the nucleus. Now, atomic number is specific for each element. So elements of oxygen will have, I think it's 8 protons because its atomic number is 8. If you look at fluorine, its atomic number is 9. It has 9 protons. If by some magical miracle I could reach into a fluorine atom, remove one of its protons, it would then become oxygen. It's the number of protons that dictate what an atom is and what element is part of. So the atomic number is the number of protons found in the atom of an element. If the protons change, the element changes. All right? Now it's usually found in the top part of the square for the periodic table, but it's periodic table dependent. It's very kind of, how do you want to say it? It's very manufacturer based. Some manufacturers put it in the center of the square, like you see here. Some manufacturers will put it over here. Some manufacturers will stick it over here somewhere. Inside the square, of course. It'll be somewhere here or here. So be mindful of that. If you ever wonder if you're looking at an atomic number, every periodic table typically has a key that tells you what everything means, or just look for the numbers that are going in order. 1, 2, 3, 4, 5. Those are the atomic numbers. Now, atoms are neutral. Write that down in your notes. Atoms are neutral. Atoms are neutral, which means the positive charges equal the negative charges, which means the number of protons equals the number of electrons. Very simple, but very critical that you understand that. If you have an atom, say for example aluminum, it has 13 protons, it must have 13 electrons if it's an atom. The overall charge of an atom is 0. Atoms have no charge. Their overall charge is 0 because the protons equal the electrons. All right, here's a study check. Really simple study check. I want you to pause the video, take a moment, figure this out. It's not hard. Grab your periodic table, find the atomic numbers, find the number of protons, find the number of electrons, and pause the video. Come on back when you're done, and I'll go over it. Okay, welcome back. All right, so now nitrogen. What's the atomic number of nitrogen? It looks like 7. Let's find zinc on the periodic table. Looks like 30. And let's find sulfur. Sulfur looks like, there it is, 16. These numbers were found on the periodic table. I didn't memorize them. I haven't memorized them. I'll never memorize them. I just look at the table and get it from there. So the atomic number is 7, so the number of protons for nitrogen is 7. The number of protons for zinc must be 30, and the number of protons for sulfur must be 16. Remember, atomic number equals protons. Okay? Now, these are elements, so these must be neutral. So the number of electrons for nitrogen is 7, electrons for zinc is 30, electrons for sulfur is 16. Remember, atomic number equals the number of protons, and protons equal electrons in atoms. We're talking about elements here. I know from the question, it's right here. So therefore, I'm talking about atoms. Atoms are always neutral. Mass number. Now, mass number is a very, very simple concept that a lot of people, for whatever reason, get wrong. It's very simple. Mass number is simply the number of protons plus the number of, not electrons, but neutrons. That's the formula for mass number. So mass number is the number of particles, subatomic particles, in the nucleus of an atom. And it's always a whole number. You can't have a fraction of a proton, you can't have a fraction of a neutron. It's the protons plus the neutrons. Now remember this and take this to heart. The mass number, first of all, is always a whole number, and it does not appear, does not appear on the periodic table. Now when you're looking at the periodic table, you're probably looking at a number that's below the element symbol, and it's probably a fraction. Like for oxygen, it's like 16.00. That is not a mass number. That's called atomic mass, something we're going to get to later. Okay? But for now, mass number is the number of protons plus the number of neutrons. It is a whole number, and it does not appear on the periodic table. Here's a study check for you. An atom of lead has a mass number of 207. Remember, mass number, I'll give you a little hint, mass number equals number of protons, I'm just going to call that P, plus the number of neutrons. So there's the formula you're going to need. You have to know that for exams. Mass number of 207. How many protons, how many neutrons, and how many electrons are there in this atom? Grab your periodic table, go ahead and try this problem, pause the video, come on back when you're done. Alright guys, welcome back. Now, 207, mass number of 207, and we're talking about the element lead, Pb. So let's find Pb on the old periodic table. We find that the atomic number equals, let me just double check my periodic table here, 82. So we know for part A, the protons equals 82. So we got part A done. Part B, let's leave that till the end because that's a little tougher. Let's look at part C. Part C, how many electrons are in the atom? So it's an atom, so we know that it's neutral. So we know that the number of protons equal the number of electrons. So the number of electrons must also be 82. Now, part B. We know that the mass number equals the number of protons plus the number of neutrons. So if we want to know the number of neutrons, we simply have to rearrange this formula real quick. Subtract the number of protons from both sides. So that's going to become number of neutrons equals the mass number minus the number of protons. Okay, sorry I made that a little messy. Let me make that a little prettier. Oops, sorry about that. Get rid of that real quick. I'm just going to put number of P there because I'm getting a little short on space. P stands for proton. Okay, so now all you got to do is put 207, which is the mass number, minus 82, which is the protons, equals, grab up your calculator, let me grab mine real quick. 207 minus 82 equals, number is 125 neutrons. All right, pretty fundamental question, a very easy question, I think. I hope you didn't have a hard time with it. If you did, you might want to go back in the video a little bit and review what we talked about. All right, now electron energy levels. What I'm going to try to do here is I'm going to try to take a very difficult concept and distill it down to its essence so that you guys can just understand what you need to know. Electron energy levels are a big topic, fascinating topic, but we just don't have the time, nor do we have the background to go over that in this class. So let's just break it down to its fundamentals. Electrons fit into these things we call energy levels. They're basically discrete levels where electrons can be found. Okay? Now these things are called quantized because there is no, well, simply said, they're just quantized, which means they have certain energies they can be, and there's other places they just can't be. It's a very complicated thing. But just remember that electrons fill in levels. level 1, which is called shell number 1, level 2, which is shell 2, shell 3, shell 4. These are energy levels. And the further away you get from the nucleus, the less strongly held the electrons become. This is kind of how it works. So we're not going to go over that. That's a little bit too challenging for this class. So what I want you to be able to do is write these things called electron arrangements. Now, in order to fully understand how electron arrangements work, you have to kind of see these electron levels. So let's put this dot right here, and that dot represents the nucleus. That's the nucleus of the atom. That's where all the protons are. That's where all the neutrons are. And then just draw a circle. And this circle is not a flight path for an electron. It's simply an energy level. And what the electron energy levels say is that there can be electrons in here. This is called shell 1. And inside shell 1, you can have 2 electrons. E negative is an electron. 2 of them, max. Okay? So that's like prime real estate. 2 electrons max. So somewhere in here, there's 2 electrons. We don't know where they are. We just know they're in there somewhere. Okay? So don't worry about where. They're just somewhere inside of shell number 1. Now, there's a second energy level. Remember, these are just quantified energy levels. They're just there. Okay? Don't worry about how or why. They just are. This is called shell number 2. And in shell 2, there are 8 electrons max. Okay? No, you can't have any more than that. You can have less than 8, but you cannot have more. All right? So let's grab. So here, let's just put a couple of electrons here. One over here, 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 here. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 electrons maximum can be in the second shell. Okay? It sometimes helps to think of these shells as streets. So the first shell would be like the first street. So if you want, you could call it A1A, down by the beach, where the nucleus is the attractive force of the beach. And then the second shell maybe is Federal Highway. You're moving a little further away from the beach. The streets get bigger. Energy levels are a little higher. Now let's do one more. There are more than 3, by the way, but I'm just going to do a third shell. So here's the third shell, or shell number 3. Now on the shell number 3 is a little bit strange. There are 18 electrons max. But we're going to deal mostly with 8. Now the reason I'm telling you that there's 18 maximum is because there's one question that I usually put on the multiple choice, and it asks the third energy level of an atom has how many electrons maximum? And the answer is 18. It definitely has a maximum number of electrons of 18. No question about it. But generally speaking, shell number 3 can also stop at 8 and be relatively stable. Okay? It can hold 18. No question about it. But in this class, we're always, or almost always, going to stop at 8. Okay? Level 3, or shell 3, is where things get really interesting. And if you're interested in this kind of chemistry, I would recommend you take General Chemistry 1 and 2 here at Broward. That's where we really go over this kind of stuff. Okay? But for now, shell number 3, maximum number of electrons is 18, but typically we're going to stop at 8. Okay? And that's how shells work. So out here on the third energy level, there would be between 0 and 18 actually. Remember, it can be 18, but we're usually going to stop at 8. Okay? Now, that all being said, why do we need to know all this? Well, we need to know all this so we can talk about where electrons are living inside of an atom. So for example, let me get an eraser here and erase some of this stuff. Come on, there we go. Just erase this real quick so we can have some space to work with. If we're talking about an atom, say of hydrogen, hydrogen has how many electrons? Well, we don't know. We have to go to the periodic table and find out, right? So hydrogen, we find out, has 1 electron. Now, you have to remember, when atoms fill up the area around electrons fill up an area around a nucleus, they want to be as close to the nucleus as possible because that's where all the attractive force is, right? So when 1 electron is moving into an atom and there's only 1 electron, that electron will be on the first energy level. So what I want you to do is just write the number 1. And that tells me that there is 1 electron on shell number 1, let's say. Okay? Now remember, shell number 1 can hold 2 electrons maximum. 2 electrons maximum. So helium, which has 2 electrons, because its atomic number is 2, you would simply write 2. And that tells me there are 2 electrons on shell 1. But now at this point, remember, shell number 1 can only hold 2 electrons max. Once you get 2 electrons moved into an atom, you can't put any more electrons on the first shell. You have to now move them out to the second shell, the second highest energy level. So for example, lithium. Lithium, you would write, because lithium has 3 electrons, right? You would write 2, 1. And this is telling me that there's 2 electrons on the shell number 1 and 1 electron on shell number 2. That's what it's saying to me. Now remember, shell number 2 can hold maximum of 8. So let's just jump down to neon. Neon has 10 electrons. Oops. Okay, so that's going to be 2, 8. 2 on the first shell. And 8 on shell 2, right? Now at this point, shell number 2 is full. So now we'd have to go to the next shell. So let's say, for example, let's say we want to do, I'm going to erase this top one here. Let's say we want it to do the electron arrangement, say, of silicon. So silicon has 14 electrons. Well, we have to have 2 on the first shell, 8 on the second shell. Now if we add this together right now, we have 10 electrons, right? So we have 4 more electrons we have to actually find a home. Well, there's 10 and we have 14, and we know the third shell can hold maximum 18, but usually 8, so just put the 4 there. 2 on the first shell, 8 on the second shell, 4 on the third shell. All right? So I hope you're kind of getting it, right? Remember, all the electrons add up to the atomic number. Okay, atomic number is the number of protons. So the electrons should add up to the number of protons. Should be neutral. Okay. And here's another slide with a lot more electron arrangements that you can look at. But what I really want to do is get to a problem. I want you guys to try this on your own. Try determining the electron arrangements for the following atoms. Pause the video, try it out for yourself, and come on back when you're done. All right, guys, welcome back. If you haven't had a chance to do this problem yet, pause right now and go ahead and do it. So I'm going to go over it right now. All right, carbon. Find your periodic table, look up the atomic number of carbon. You'll find that it's got 6 electrons. Let me get rid of that. I keep writing it wrong. There we go. And while we're here, let's switch colors. Let's do blue. 6 electrons. Look up silicon. Silicon has 14. I guess I did that one for you, didn't I? Oxygen has 8. Nitrogen has 7. All right, for fun, let's just change color. Let's go black. So we know that carbon has 6 electrons, so we know that's going to be 2, now be careful. How many would be on the second shell? 4. 2 plus 4 is 6. Silicon, 2 on the first shell, that's full. 8 on the second shell, that's full. That's only 10. 4 more. 2 plus 8 is 10, plus 4 is 14. 8 electrons, well again, 2 on the first shell, 6 on the second shell. 2 plus 6 is 8. Nitrogen, 2, 5. 2 plus 5 is 7. So on nitrogen, 2 on the first shell, 5 on the second shell. Oxygen, 2 on the first shell, 6 on the second. Silicon, 2 on the first, 8 on the second, 4 on the third. Carbon, 4 on the second, 2 on the first. That's how this works. Now, if you didn't get that right, you need to go back in the video a little bit and review what I've done. Look at the examples I did before this. Maybe even try to look at this example, try to figure out how I got these numbers. Go back and review the video again. It's really not hard, but you have to get it right because this is a kind of a fundamental thing we're going to need going forward. All right, trends in the periodic table. Trends in the periodic table. Uh-oh, you better write that down right now. Valence electrons. Ooh, we got to make sure we can do this. That's a fundamental concept in chemistry. All chemistry is explained with valence electrons. And group numbers are on the same slides. This must be important. Okay, valence electrons are the number of electrons in the outermost energy level. Write that down, put like stars around it, underline it 3 or 4 times. That's important, okay? Valence electrons are the number of electrons in the outermost energy level, okay? And the group number gives the number of valence electrons for the representative elements. Remember, representative elements are anything that's not a transition metal, for the most part. There's exceptions to that, but for the most part, that's true. Okay, so valence electrons are the outermost electrons, and the group number gives the number of valence electrons. Okay, oops, let me talk about a few things here. If we have, say, an element of fluorine, so fluorine's in group, look on your periodic table so you can prove this to yourself, fluorine's in group 17. But now wait a second, we just got through saying that the group number gives the number of valence electrons. Fluorine certainly doesn't have 17 valence. In fact, if we do fluorine's configuration, it's 2, 7. Okay, well, it still tells me the group number still tells me the number of valence electrons. You just have to be careful with how you read it. Whenever you look at a group number of a representative element, a non-transition metal essentially, you'll see that some of them have like a 1 in front, 17. Well, just ignore the 1. It's 7. Does that make sense? Let me say that again. When you're looking at a group number and say it's a teen, say 13, 14, 15, 16, or 17, or 18, you simply ignore the 1. You just look at the second number. Okay? So fluorine has 17 electrons. Let's look at argon. Argon is in group 18. Look on your periodic table, prove it to yourself. Argon's in group 18. Well, according to my rule, you just ignore the 1. You ignore it. So argon should have 8 valence electrons. Argon actually has 18 electrons total, so Ar would be 2, 8. That's 10. 8. 8 valence. 8 valence. Okay? You simply look at the second number. Let's do one more. Let me get an eraser out here. Let's do like, what's a good one? How about sodium? Sodium is in group 1. Now there's only one number in group 1. So that number, you just look at that number and you say, okay, sodium should have 1 valence electron. It has 11 electrons total, so sodium's arrangement would be 2, 8, 1. So for group 1 and group 2, you don't have to ignore any numbers, you just look at the group number. So sodium has 1 valence electron. Let's do another example. Oops. Let's do a group 2 element. Let's look at beryllium. Beryllium is in group 2. It's got 4 electrons, so it's going to be beryllium will have the electron arrangement 2, 2. So it's in group 2. It should have 2 valence electrons, and indeed it does. So here we go again. Group 1, group 2. Just read the group number. All group 1 elements have 1 valence electron. All group 2 elements have 2. Group 13 through 18, you simply ignore the 1 use the second number. So group 13 has 3 valence electrons, group 14 has 4, group 15 has 5 valence, and so on until you get to 18. This trick does not work for the transition metal, so don't try to apply it in group 3 through 12. It doesn't work there. Okay? This only works for group 1 and 2, 13 through 18. Now, nobody wants to draw electron arrangements all day. Nobody. In fact, chemists are very visual people. We like drawings and we like to use symbols to represent things. It makes life easier. And that's why we have this thing called the electron dot symbols. What the electron dot symbol is it's just a way of representing the valence electrons without actually writing any numbers down. So now, instead of numbers, we're going to use dots. And these dots are called single electrons. One dot, one electron. That simple. So here are the examples of aluminum. Aluminum has 13 electrons, 2, 8, and 3. It's also in group 13. So we know it has 3 valence. So then we just take aluminum. We just take aluminum. 1, 2, 3. Okay? That's simple. Very, very simple. Because it has 3 valence electrons, we drew 3 dots around the aluminum. Notice how I drew mine a little different than the slide. It still says the same thing. So here's an example of magnesium. Magnesium's in group 2, has 2 valence electrons. These are all acceptable dot arrangements of magnesium. However, notice we don't have this as acceptable yet. You would not draw that. That is not acceptable. The electrons are not paired. They're actually separated from each other. Okay? So 2 valence electrons. Every one of these drawings has 2. Okay. Write the electron dot symbol for each of the following elements: chlorine, carbon, and nitrogen. Remember, look at the periodic table. Look at the group number. If there's more than one number in the group number, say you have group number 14, you have 4 valence electrons. You need 4 dots. If it was nitrogen or chlorine, you'd need look at the group number and figure out how many valence electrons it has. Now, chlorine and nitrogen are a little tough, so maybe I should do one more example for you before I let you do the study check. So I'll do argon. I'll do the symbol for argon. So argon has 8 valence. I'll just call it VE, okay? Valence electrons. So I'm going to do for argon. Argon's a little tougher than the ones you have to do here. So argon, 8 valence. So I'm going to start at the north side. North, south, east, and west. Okay? So those are only 4 of my 8. The rule is this. After you get to 4, you get to the 4 corners of the map, if you will, north, south, east, and west, then you must double them. You have to put them in pairs after that. So 5, 6, 7, 8. After 4, north, south, east, and west, then you have to double them. So 5 through 8 valence electrons, you have to start having doubled up electrons. And these bad boys here are called lone pairs. I have no idea why they're lone if they're in pairs, but they are. Lone pairs, okay? After 4, you must pair your electrons. They start to pair up. Don't worry about why that is, just it is, okay? After 4, electrons must pair. So, in chlorine and nitrogen, you should have at least one set of lone pairs, probably more for one of them, and carbon shouldn't have any lone pairs, okay? So those are big, big hints for you guys. So pause the video and try this question now, and when you come back, we'll be able to work on it together. All right, guys, welcome back. Let's do chlorine. Chlorine is in group 17, has 7 valence electrons. Carbon is in group 14, has 4 valence electrons. Nitrogen is in group 15, so it has 5 valence electrons. If you didn't get that far just yet, pause the video again. Try it now from here. All right, here we go. Chlorine. North, south, east, west. That's only 4. We need to put 3 more in here. So I'm going to grab another color. Two, 4, 6, 7. 7 valence electrons, just like that. So it has 3 lone pairs and 1 single electron. Carbon, 4 electrons. 1, 2, 3, 4. So there's carbon. Carbon has 4 valence electrons, so it doesn't have any lone pairs. Nitrogen, north, south, east, and now west. That's only 4 though, right? We have to have 5. So put 1 right there. Okay? 2, 3, 4, 5. The number of dots should add up to the number of valence electrons. Okay, a couple of definitions here, and then this chapter is over. Atomic size is determined by the atomic radius. So now, if you will, let's pull my face up here. Let's have a look at me here. All right, imagine, if you will, my finger right here is the nucleus, okay? So the atomic radius, the distance from the protons, which will be in here, and say to my pen right here, as this distance between my pen and the fingers, remember my pen will be the electrons, the valence electrons, right? As that distance increases, the atomic radius increases. This is the nucleus, this is the electrons, the valence electrons. Now as this pen gets closer and closer and closer and closer and closer to the finger, this is my neutrons, remember, or neutrons and protons, the nucleus, the atomic radius shrinks, okay? So as the valence electrons get further away, the atomic size of the atom is increasing. As the valence electrons are closer and closer and closer to the nucleus, pardon me, I'm all stuttery now. The atomic size is decreasing. All right, so atomic size increases as atomic radius increases. Okay, so nucleus, electron, valence electrons. As they move out away from the protons, the nucleus, atomic size is increasing. As they get closer to the protons, atomic size is decreasing. Now the white pen represents the valence electrons. All right, so now let's look at some rules here. The atomic size will increase for the representative elements from the top to the bottom of the periodic table. In other words, as you go down a group, atoms get larger. So for example, if you look in your periodic table, which you should have with you right now, if you look in your periodic table, look at fluorine and look at iodine in group 17. Fluorine is on the top of the table, iodine is towards the bottom. Fluorine has a much smaller atomic radius than iodine. Now let's think about that for just a minute. Iodine is on period number, what is that, 5? Period 5. 1, 2, 3, 4, 5, period 5. So it's actually using the 5th energy level, the 5th shell, to fill with electrons. It's got a lot of electrons. It's got to fill a lot of electrons in there. Fluorine, however, is on the 2nd period. So it's only using the 2nd shell. So its valence electrons, remember we're only talking about valence electrons here, its valence electrons are really close to those protons. Now the other rule is it decreases within a period, going left to right. So if you look at the periodic table again, and you start with lithium in period 2, element number 3, and you go all the way across to fluorine, elements actually shrink as they go from left to right. Okay? So the atomic radius of lithium is much larger than the atomic radius of fluorine. And that has to do with the attractive force of the nucleus. So as you get more protons in your nucleus, atoms on the same period get smaller. But you have to be on the same period though. Okay? Ionization energy. Now, ionization energy is defined as the amount of energy required to remove an electron. To remove, not to add, but to remove, okay? And ionization energy actually will decrease going from right to left. So it's kind of the opposite of atomic size. The larger you get, the easier it is to pull your electron away. The smaller you get, the harder it is to pull your electron away. So if you look at the lithium and fluorine example that we just talked about, lithium compared to fluorine is very easy to take an electron from. Fluorine, because it's much smaller, so the electrons are held closer to the protons, it's much more difficult to pull its electron away. All right? So going from right to left through a period, ionization energy gets lower. Going from top to bottom through a group, ionization energy gets lower. And that's just how it works. Okay? And here's a little slide to kind of hammer home what I was just saying. Ionization energy increases going from left to right through a period. So the larger elements have a smaller ionization energy. The smaller elements have a bigger ionization energy. Smaller, larger, easier to ionize. Okay? Ionization energy is decreasing down a group. All right? Now this video went a little bit longer than I wanted it to, but we did finish chapter 4 right here. So now look for chapter 5 videos to be coming very, very soon. And if you need to, rewatch these videos, redo all the problem checks. Don't let this stuff get away from you, because chapter 4 is a very fundamental chapter that you really have to understand. Now with that, I would wish you good luck, and I will see you in class.